Sorry about all the logistic, but let's just start. Okay. So I want to start with the evolution of the modern data stack. Um, I have been working in the data industry or big data world for almost more than a decade. So if 10 years ago or a decade ago, if you're talking about the data storage and also the computation, it's mostly just Hadoop, and all the data is stored mostly in HDFS because that is mostly the most scalable way to store data in a cheap way compared to commodity hardware. Okay, so Hadoop, the entire Hadoop ecosystem is based on the idea that we have a deeply coupled Hadoop computation and Hadoop storage. Okay, and also most of these data warehouse, they're built in the on-premise data warehouse with on-premise HDFS as their storage. And most of computation is in a single region or in a single cloud. But if you take a look at today, the landscape is quite different. We get a separated compute and storage, and on-premise HDFS is mostly replaced by the cloud or in-cloud data lake. And also we're seeing more and more customers or people in the field are doing multi-region or hybrid cloud or multi-cloud as their solution to deal with the two-sided architecture. So definitely there's a reason behind why we're seeing this evolution. In this way, with the separated compute and storage, with the data lake, with the multi-region, you get more elasticity and also cheaper, more scalable, and oftentimes it's more easy to scale to keep the negotiation power, especially you're embracing multiple different clouds. Okay, does that solve everything? Perhaps not. So especially we are seeing a lot of the I/O challenges associated with this, and when data is remote or through network to go to the compute. And if you take a look at the design philosophy in Hadoop, where data locality is one of the main idea behind, in this case, data locality is more or less missing or completely missing in this picture. Okay, so let's just take a closer look. What's the implication of a missing data locality? We have these different dimensions in performance, in cost, or in reliability. So in terms of performance, with the analytics cycle, high query latency may be incurred because retrieving remote data, and for model training, and training can be slow because loading remote data is required for the, sorry, I forgot to open my camera. Let's just turn on my camera. Yeah. So listing and also a lot of small files can be also another reason for you to see slow performance. And on the cost side, being different from the cost model or the pricing model from a on-premise data storage, in the cloud APIs, the operational cost in APIs can be actually non-trivial, sometimes significant. If you call an API to get the data or list the data, list the bucket from the cloud storage, that is actually charged based on number of API calls. In addition, the cross-region data transfer, sometimes we call this egress cost, is also another source of like operation. Besides, especially in the days of I'm just back from GTC and everyone is talking about GPU, of course, like in GTC. So GPU cycle is still considered as a very expensive resource, and GPU cycles can be wasted if we are waiting for the data. Another important or interesting thing phenomenon we see is about the reliability, the data reliability, including job failures because this unstable data access, or sometimes it's because we see, for example, in Amazon, you can see this exception 503, especially because you are sending an overwhelming number of queries to the backend storage. So this actually becomes some issues for a few customers or users we see in the past. Okay, these are the data challenges. On the other hand, system design is all about trade-off you make. Okay, so one interesting, especially is like 10% of the whole data, entirety of the data is the hot data, or sometimes we call this a working set. So it's essentially, given this observation, can we just think, hey, can we add a caching layer here to in between the computation and storage to help you make this hard data or the working set closer to the computation and reduce the cost and reduce the reasons why you are not able to read data reliably. Okay, so if this is like a hypothetical view of the latency, the composition of the latency, you got to compute and doing I/O and waiting for the I/O for next compute doing the I/O. Sorry, next I/O, right? If we are able to reduce, so that's the total cost, total runtime for the job. If we're able to reduce the I/O cost, then perhaps you're able to reduce the total job running time too. Yeah. And aside from that, given GPU is often the bottleneck, or sometimes the GPU cycles can be expensive, with the caching, I'm talking about a training case, when the GPU is idle, it's definitely not really well utilizing the GPU, the resource, okay? So by reducing the IO portion in this total execution time, we're able to reduce make the GPU more busy and most of the time, okay? So to increase the GPU utilization. Another benefit is, hey, by having this caching layer between the compute and storage, we can reduce the frequency to retrieve data, especially for the high volume get or list operations. We have seen in actually quite a few different users that these operational cost for APIs, data APIs, is actually phenomenal. So with cache, we're able to basically read the data once or list the bucket once, and then make it in the caching layer to enable the fast access with the hot data cache. Okay. By the way, if there's any questions, feel free to raise that in the Zoom chat or just to speak out. Like I prefer to answer questions online. Okay. Improve reliability if we can reduce the job failures. Including 503 service unavailable exceptions, and that can actually make the job more reliable for a lot of times. Okay. Okay, so what is the observation so far? The evolution of a modern data stack process actually poses the data locality challenge. So we can think of how to tackle this problem in terms of performance, cost, and reliability for your data platform. And a very naive, very straightforward solution is to have a caching layer there to basically reduce the cost or improve the performance and improve the reliability. And we have seen a lot of data points to show that this works well for both analytics and AI type of workloads. For today's talk, I will just mostly focusing on the AI training workloads. Okay. This is a very typical life cycle for modern ML data platform. So data is stored in one of these solutions or the storage solutions. It can be S3 or Azure or GCS or even HDFS. So it has been the training cluster sometimes it's located or sometimes it's not co-located with this storage and can read the data. And then by certain operations, iterations, and then checkpoint or even like output the final model back to this storage. And the models can be also as a source for the serving cluster. This is often used in the online machine learning platform and to inference, basically output a prediction based on the models and also user queries. So that's a very typical way to do this. Interestingly, because the scarcity last year of the GPU, the global shortage, we have seen actually quite a few users, many users telling us we are using different cloud or different data centers to do this, okay? In one cloud or in one data center, we're doing this training, and in another data center or cloud, we're doing inference because that's where I can get GPU. Well, how do you do this? How do you enable data access from the cloud storage? there are different ways. So let's just go this through one by one. Option one is you can read from the cloud storage directly. Today, most of the platform or most of the training framework will support this. Okay, it's easy to set up. But the problem is the performance. Okay, for model access, they are repeatedly pulled from the cloud storage. For the training data access, the reading data can take more time than actual training because the cloud storage may not be fast enough to serve this training data access. So we do have one demo here. Actually, this shows in a ResNet 50 training job on S3, it actually takes 80%, more than 80% of time spent on data loading. And this is by PyTorch. This is in PyTorch. And one of the reasons we see this is because we're doing ResNet 50 based on ImageNet as the input. And there are many different relatively small files on the order of millions of small files as images of images as the input. Okay, so this is not the best use for a cloud storage if you have a lot of small files, small images to train your model. And it could be the bottleneck from I/O. Option two, we see this also often that especially for users who are running a relatively small size of the training cluster, they just copy the data to the local before training. So data now is local, you get a fast access local as fast as a local SSDs or local storage. But the problem is that management is hard and you have to manually download the data and manually delete the data. When you have a relatively small number of machines or sharing with a small number of tenants with the team members on this infrastructure, it might be doable. But once you have a more like on the order maybe hundreds of different machines or with many different other users, you may or may not know in your corporation, in your organization to share the resource. This could be hard. The third limitation is local storage space is limited. You can have maybe these days 10 terabytes or 20 terabytes of local SSDs. But if you have the data sets larger than that, then you would perhaps run into issues. The limitation is very obvious. Option three, we have seen, for example, there are solutions like S3FS, which is a gateway to translate S3 API into a local POSIX type of API with built-in local cache. And we also have a similar solution we call the Alluxio Fuse SDK. So this can reuse the data if it has been already cached locally, so you get a fast access and less cost. But the caching layer, so you don't have to, with this caching automatically retile data or load data, you don't have to manually delete or to remove data. But still, the cache space is limited. If the data set is huge, you still cannot fit if it's too large to fit the local storage, and then you still have reduced efficiency. Okay. And the fourth option is you have maybe a distributed caching layer and you have this data partitioned or sharded across different workers. And on the application side, you can read this cache rather than going to the storage directly. And typically, this is a way, when you have a platform, you need to really think about, hey, how do I reduce the cost? How do I improve the performance? Or how do I make sure the entire data loading and data downloading or data management is automatic. So definitely this is a more intelligent, but also incurs cost and complexity in operation. So that's the typical 4 different ways you can do things. You can achieve your goals. Okay. Challenges. First thing, performance. Pulling data from the cloud storage can hurt the training or serving. So we try to avoid this definitely. Repeatedly downloading data from cloud storage is costly, and if you download data across different regions for the cloud, it can charge you extra amount of money. Reliability, and we want to make sure every service is cloud is on, and usability, like manual data management is unfavorable for different users. So that's the just take one step back. These are the different dimensions we're thinking through this to evaluate the different options. But just still, like I talked to many different users. Once they have just like one or two servers, they still prefer just to go to the S3 or the cloud storage, just download the data and move them to their storage, to the local storage directly and use that. Especially when they are small, the data size is likely to be small, and it's just easy and it's almost free, right? So, but again, once this goes to a platform, if you have a platform to design, if you're an architect to design a data platform for your machine learning workloads, that cannot be scalable. Okay, so I want to take Alluxio as an example how we implement this as a distributed caching layer for applications, for Python applications. So first of all, it's a distributed system. So we call the process called worker. Each worker is a process that's running on the machine to manage its local storage. And many different workers are coordinating together using the consistent hashing to shard the data and metadata on different workers, so the client knows where to get this particular piece of data or metadata. So you have a local storage, and that is limited by the local storage size, but combining all these workers, you get a much better space resource, right? And especially if the sharding function is good enough, you can basically the hashing function is good enough, then you just have a linear scalability in terms of how much data you can store. And in this way, in the early design, we have a component called master. We removed it right now. And so no more single point of failure, kind of good reliability. And also because there's one less hop compared to a lot of design like HDFS, we just for the data go to the worker directly, and the performance is good, and it's linearly growing. So, but if you're adding more workers, and this can be easy for user to manage the data. Okay. By the numbers, we are able one worker to support 30 to 50 million files, and it scales linearly, easy to support 10 billion files. We have a pretty good high availability and no single point failure. We have fast data loading and also support cloud native operators and, for example, CSI Fuse for data access management. This is the way, like, for example, if you use a Fuse, if you expose Alluxio as a distributed caching layer to your Python applications, you have different choices. Fuse is one way. It's a little bit more heavyweight, but it's mostly very universal or generic. So essentially, we expose this logical caching system as a local file system to your machines, to your applications. So you can run cat, you can run Linux command like cat, ls, you can open a file, and very low impact for the it's very transparent and low impact or no implication to the end users. And in this way, you can just like you are using a much larger logical space consisting of a lot of space from individual workers. Okay, and we provide a CSI or Fuse, so you can turn this remote data set in the cloud into a local folder through Fuse and use a CSI to launch the Fuse pod only when the data set is needed. So this is just one example, like how you can do this option 4. Previously, I mentioned different options to load data, and we provide this solution. And we, by the way, Alluxio is open source too. So it's originally from UC Berkeley as a research project. Okay, so in the later part of this talk, I will talk about how we do the data access management for PyTorch for other Python applications. So this is basically what we do, how we integrate with PyTorch. The easiest way is through the Fuse interface. PyTorch can directly read or load data through this, and this is the client's. This cache client is basically referring to the Fuse client. And with this Fuse client, we're able to connect it to a set of different cache workers, and the cache workers can just have data sharded and stored in each individual worker. And the PyTorch can just read the data or load the data or even write the data, just like writing a reading from local directory, while it's actually engaging with the distributed system like Alluxio. So this is one way. We have some numbers to show for data loading If you have a CV data loading with Alluxio fields, IOPS per second is about 10K. With S3 fields, this is less than 5K. And if you go to AWS S3 directly, that's about like a little bit more than 1K IOPS per second for ImageNet. For NLP, so we have this is on the data set of Yelp review. We also evaluated different ways. We called Alluxio fields. We also have our own RESTful API and S3 API. You can see this is because this is the file, the input file is larger here. So we just measured by the megabytes per second in terms of throughput. Okay, so the S3 API or RESTful API provided by Alluxio is larger. It's much larger than the S3 FS fields or AWS. So essentially, we show, okay, data loading, you can just benefiting from this having this caching layer between the application, the Python application like a PyTorch and S3. So we have this GPU utilization improvement. You can see this is from a TensorBoard. The execution time previously is more than 80%, which results in 17% GPU utilization, 17% GPU utilization. But now with this caching layer, we are able to reduce the data loading time from 80% down to 1%, which is 80x. And the GPU utilization is increased from 70% to over 90%, which is 5x. So this you can see for certain type of workloads, especially like if you're involved, it's involving a lot of small files and from the cloud, this can be really efficient. Okay. So I was talking about using the Alluxio as a caching layer for PyTorch using the fuse, but there are different ways to do this for Python applications, and this is also work in progress. I'm just sharing the work in progress and see. I want to get input from the audience that how would you like to use if you have some Python applications, whether you can benefit from this, whether this is a bottleneck at all, or there's some ideas you want to advise us. That's awesome. Okay, so like taking array integration, for example, we're trying to integrate with array instead of having the fuse interface. We're doing a fsspec interface to integrate with PyArrow and with array because array data loader is based on PyArrow. So essentially, we implement Alluxio implementation of fsspec, and we have the Python client embedded in this Alluxio implementation of fsspec. And this Alluxio Python client can talk to the RESTful API on different Alluxio workers, or you can load the data, or you can just read the data. So that is pretty much like the idea, like instead of having another fuse, you use the CSI or use some other approach to launch the fuse. We leverage the fsspec API or library widely used in Python world to enable Python application, like in this case, Ray, for example, to talk to the Alluxio distributed system. So that's one way to think about it. Okay, so some benchmark in terms of small file throughput, in terms of image per second. With Alluxio, we're able to, when we are using large memory size for this Ray benchmark, they are about the same. But when we are seeing smaller memory allocated to Ray object store, Alluxio can provide a much higher small files throughput in terms of images per second. So this is on the 130 gigabytes ImageNet data set. And with 4 training workers, 9 processing reading, and the active object store is about memory is about 400 to 500 meg. Okay. More data on the large Parquet files in terms of image per second. We see the Ray object store memory is increasing. Both using S3, reading from S3 or from Alluxio can increase, but we're about like twice the performance as a reading from S3 directly. Okay, long story short, this is a work in progress. We're showing that with a fsspec, that's one of the most popular Python applications to talk to different storage. And we're able to add transparently a caching layer between Python applications and the storage. And you can even have the command line you can run to load the data before you run your Python applications into this caching layer. So in order to reduce the data loading time. Okay. Further benefits regarding the cost saving. So with this Alluxio in between, the egress cost is almost zero after data loading, and the caching ratio you can see is pretty high. Most of the data is cached. Okay. And we can also do this for API calls and S3 operations. Okay. Yeah, this is last slide. Basically, I want to show one use case that how we are able to reduce the 30% time to compare to consuming from cloud storage by adding this virtual layer, caching layer. And for autonomous driving company, so essentially they have this training cluster. They're having different clusters to store the data. So the training is based on data sets from different clusters, cluster A and cluster B. By reading this directly from class A or class B, it's not inefficient. So by adding the layer here closer to the GPU nodes, and we're able to reduce the time for this training and also scale the GPU utilization from 30 to 50% to more than 90%. Okay. Okay, so that's it. That is my last my slide. Any questions? Actually, especially I would like to hear your opinions about like I don't know how many of you are Python developers, and do you even see this becomes a bottleneck in I/O? And what is the life cycle? I would be more than happy to discuss it with you.